classes that you typically take if you're going to be a science major. And then do a couple of examples of topics that we talk about at some point during the year in Math 115, 116. So I don't know how much math any of you have done. So you've all done Algebra 2 and trigonometry and pre-calculus and maybe some calculus? Some? You loved it? You have mixed feelings? Okay. Well, nice thing about university, college is you get a chance to start over. Math is a subject that everybody's got an opinion about. Right? It's one of those things, because we've all been exposed to it from the time we started school. But what we do in university is a little bit different. And I'm just going to go through the beginnings of a document that you should have access to. I think I sent it to you, and
yes,
this is a whole bunch of information, far more than you need, about the options that you have and the kinds of decisions that you might make in the fall when you register. So there are basically two flavors of mathematics that you use in science classes: calculus and probability and statistics. So both are important as far as tools in the sciences. It could be that probability and statistics is in fact a bit more important. It's the kind of thing that you use much more frequently in areas outside of your classes. The standard calculus sequence for people who come in without AP credit is Math 111, 112, Calc 1 and Calc 2. Don't presume any calculus, just presume a strong pre-calculus background. They serve students who want to learn economics and physics, some chemistry, or math. Math 115, 116 is different in that it's designed specifically for biology majors. It's required by the BS in the BS program in biology. It's recommended by NBB, neurobiology. It starts off the same as a standard calculus class in Calc 1, but then we move a little bit away from typical sort of physics examples and do more with life science modeling, exponential growth and decay, that sort of in the fall semester. And the spring semester is really a lot different than calculus 2. It's quite a bit of applications of differentiation and integration, tools from calculus, modeling, and biology. For the first half, and the second half is probability and statistics. So it's a different kind of calculus class. As long as you've got a good pre-calculus background, you're prepared for either option A or option B. The other courses are higher level math courses that are typically taken by not so many freshmen. Only if you've maybe done BC calculus in high school would you do that. Then there's another set of courses that have to do with statistics. One that's new here last year called QTM 100. This is an introduction to stats. Right now it's required by social science majors, and biology is thinking about requiring it depending upon how the course develops in the near future. But for entering students this fall, the Math 115, 116 is the typical math requirement for the bio major. How many of you are thinking of a bio major? And the rest, NBB, maybe non-committed, undecided? But everybody in the program has an inclination toward doing some kind of science. You can interrupt me, honest. Ask questions. Otherwise, this will go really, really quickly. So this document's got a lot of pages in it. And it's more than you'll need to know, certainly. But I just put it in to give a flavor of what math course is like in college. First of all, placement. What sequence do you want to take depending on your interests and your background? The second thing is a 5 or 6 page information handout that I give out at the beginning of Math 115. just how you're evaluated, the expectations, that sort of thing. So one thing that might be different about how a class is delivered here versus high school is the professor will create a document like this for you, like number 2, which is and so lots of straightforward information. But once we give this to you, post it on Blackboard, the tool that's used for keeping track of courses and posting assignments and that kind of thing, then we feel as though we fulfilled our responsibility for explaining what's expected of you. So the upshot is you need to read this stuff and pay attention to it. And then the following will not happen. The day of the first midterm, someone will come into class, sit down and say, "What? I had no idea." Everything's in here. Schedule for the class. Of course, I constantly remind you when assignments are due or when exams are coming out and so on. But believe it or not, not everybody comes to class all the time. Okay, maybe I shouldn't have told you that. And so you really are responsible for keeping up with things. All the information's there. You only sort of have yourself to blame if you don't keep track and stay current. So again, this is it may be a difference between university or college and a high school class is that we post this stuff, we talk about it, and then we expect you to have access to it and pay attention to it. Another thing that you'll notice, and you'll notice this with math classes, you'll notice it with language classes, is things tend to move quickly. You have maybe only 2 meetings a week in a class, maybe 3, and yet you'll be zooming through these chapters. It's a pace that's quite a bit different than the high school pace. And the expectation is that you're doing a lot of work outside of class, keeping up, and so on. Also, you're just taking 4 classes, typically plus maybe a health or a PE. And so you really are expected to concentrate on those classes and to keep up with them. To add to that, math, like language, is really vertically organized. So what you do on day 1, you don't get to forget it on day 11. Everything is built upon what happened before. So if you're scratching your head wondering, whoa, this does not make any sense, it could be because there's something in the first week that wasn't properly digested. So here, we stand up at the front of the class at the beginning and we urge you to come and see us if you fall behind, if you have any questions about the lectures, if you just want to talk about the material in the class. So talk to us, the teachers, there are TAs, there are graders, all kinds of resources. There are also various kinds of tutoring programs available through the college, depending upon the subject and the class itself. So you should be able to take advantage of all these things if you need to.
Question?
Yeah.
Do all the math classes and everything come with lab components or only some?
No, there's only a few that do right now. 115, 116 has an extra hour a week of lab. And let's see, 221, the linear algebra class has one. But those are the only 2 at this time. So one thing is that starting this fall, that means those 2 classes carry 4 credits rather than 3 credits. The way we use the lab in 115 and in 116 is mostly for extra practice, opportunities to ask questions about stuff that's been covered in lectures, maybe some group work. Also, we do quizzing in the labs. There are frequent quizzes. You're supposed to, it's a fairly well accepted tenet of education now that frequent testing leads to more retention. Well, it leads to more anxiety too, but more work for everybody involved. So I was going to tell them, yes.
So if I do badly on a quiz, should I just keep that to myself and go back to my room and get mad at you because you didn't teach me well? Or what would you recommend I do if, under the weird circumstances, that I don't do well on a quiz?
This is a leading question.
It is.
There's only one right answer to this question. For one thing, there are lots of quizzes, and usually we drop low scores. 1 or 2 during the semester if we have, say, 10 quizzes. But the reaction to booting a quiz is to sit down with it and the solution set, the key, and first figure out where you stopped understanding, where the mistakes occurred, and then to come to see me or to see the lab instructor and to go over it. One thing that some students seem to like is getting a study group together, because you learn something best by explaining it to someone else. So if you're in a group with someone else and you're talking about a new topic, then being able to see what's causing other people problems helps you understand what causes you problems. And having to explain to someone for the 14th time why a limit is a limit, you really begin to understand why it is what it is. So, besides encouraging you to see your teachers, I'd also encourage you to form study groups and to work together with a group of peers. I know this happens very frequently in a lot of the lab science classes. And lab science classes lend themselves to this because there's so much contact. There's long labs, wet labs, as well as lectures. So it's a solution that's good for math too. Okay, so now for the content portion. If there are any organizational questions, I'll be happy to stay after and talk to you about anything that occurs to you. Yeah, this is 2:30 to 5 on the schedule?
Yeah.
We're not...
No, it's as long as you need it to be.
So,
they were all excited. They were like, math until 5 o'clock. I love it.
Hallelujah. So a few years ago, maybe the first time I taught, so the classes are either 3 50-minute meetings, or almost all of them now are going to be 2 75-minute meetings a week. 75 minutes is a long time to stay attentive. I won't say especially in a math class. But I remember an evaluation from the first semester I taught 75-minute classes. And the kids said, there was a pretty good class, but God, I couldn't stay awake for the entire 75 minutes. So we do our best to be entertaining. But usually with a 75-minute class, we'll break it up. At some point in the middle of the class, we'll say, okay, I want you to do this. So either you on your own or with the person sitting next to you, depending if it's in a small class, maybe you're on your table. Work on this problem, and then I'll ask for solutions. I won't be so cruel as to make you go to the board and present a solution, which does happen quite frequently actually in other classes. But I will ask you to explain to me how to do something. It's a way better way to stay awake than to listen to a professor talk for 75 minutes. So anyway, that was a way of saying I won't be talking for 5 minutes. All right. So now I ask you a question. In your experience, how is math used in science? Can you put this up for me? Just name some ways it's used. Yep.
Rate of population growth.
Let's start with size. So it's a measuring tool. See, you went to the second verse right away. We measure with numbers. Real numbers, counting numbers. almost anything we do involves some kind of enumeration or weighing or something, an assignment of numerical values too. And so population size would be an example. But as well as using numbers to name things like the weight or the height or the number, mathematics is also used to describe how something like a population might change, or perhaps how the length of the day might change over the course of a year. And this involves the creation of sort of mathematical descriptions for whatever it is we're interested in measuring or describing. Now, those descriptions can be very, very complicated and sophisticated. So you turn on channel, how many of you are from Atlanta? Okay, so every morning, Severe Weather Center 2, Karen Minton explains that she's going to show us a new model of what's going to happen during the day. Well, it's sort of the same as a mathematical model. It's a computer model. And what she means by a new model is you take a bunch of new data and plug it into a computer program. And that computer program is so sophisticated and beautiful that it creates the images of the thunderstorms that are going to take place over the course of the day, which has been happening a lot here lately. So meteorological models are very sophisticated models that make use of a lot of computing, but underneath there's a lot of mathematics that goes into describing how the weather is going to be changing. Simpler than that would be something like a population model. So let's take something like population at time t is given by p of t. Now, for thinking of a population of humans, then this could be a counting number, and t could be years from some base year. Or if it was a bacterial colony or growth in a chemostat or a lab device of some kind, then p of t might be micrograms and t might be minutes. Units in both for what you're measuring in time dependent on, of course, what you're dealing with. Now, there's one kind of population model that's very well known, and it starts from an assumption that's appropriate for something, say, like a single-cell organism that's growing by cell division. So, for instance, you might have something that tree. What this is supposed to indicate is that after 1, 2, 3 minutes, oh, maybe this is just 1 minute. Or maybe it's 1 hour. We have 3 divisions, 3 sets of divisions. So for every original bacterium, we now have how many? Now, what this will mean is that if the population at time 0 is, I don't know, maybe an easy number, 10, then the population at time 1 is going to be 10 times 8, yeah, 8. Okay, 2. 10 times 8 times. In another minute, how many times is this going to?
8 more.
8 more.
So 640.
now the magic of exponentiation. After t hours, pardon me, I've got this many. If I started with 10, I'll have this many. Well, that's what's called an exponential function, and this is what's called exponential growth. So where did exponential growth come from? It came from the assumption that the rate of growth in the population is proportional to the size of the population. So because the division takes place at every step, then if you just take the total number you start with and multiply by the appropriate factor, you'll get the result after so many minutes or so many hours. The magic phrase is the rate of growth of the population is proportional to the size of the population. So if you have something like bacterial growth, which obeys this, then the consequence is exponential growth. No choice. Other things obey this. What happens to a bank account would obey this. Now, the multiplying factor is not nearly as large as you will be able to. Anybody who's put money in a savings account knows that it's going to be something more like P of t is the initial principal times 1.0001 to the t. You don't get much anymore. But anyway, it's still exponential growth. There's also exponential decay. Or decrease. We often hear the phrase exponential decay because the model is being applied to the behavior of a radioactive isotope. So you've got something like carbon-14 or any other, I never remember the numbers of neutrons, so let's stick with carbon-14. And the rate of decay is proportional to the amount of carbon-14 present, which means that the equation is going to be something like C of t is the initial amount times, and now here, it's typical to use the Euler E, 2.7 something, e to the minus kt. Here I could have written this as 10 times e to the, well, it'd be silly, the natural logarithm of 8. That's just 8 again. But it makes more sense to use the integer. The typical way that an exponential growth or decay function is written is like this. And there's the variable up there making it into the exponential function. You, I don't know what, machine tools. Then I hit plot. And there's the graph. Now, it maybe doesn't look so great because the interpolation between points is a straight line rather than a nice smooth curve. But this looks pretty good. Also, beware, these axes aren't where you think they might be. This guy here isn't 0. It's the value for 5.4. But if you stared at exponential decay curves, it's not hard to believe this might be exponential decay. And what you might think about doing is trying to extrapolate a bit, but that, the way this is presented, is not very hopeful. But there is something that we can do. It's really simple and makes use of the form of an exponential function. So C of t is, exponential function always looks like some constant e to the minus kt. Where k is a positive number, this is exponential decay, t is the input variable, c is the concentration. Now, I'm not so confident about being able to guess at the exponential curve accurately enough to come up with a description of the function, but I do know about logs and exponentials. What happens if I take the log of both sides? Isn't that over?
What do I get?
Hmm?
Doesn't your ego away? Do I have that way?
Yeah, it goes away, it doesn't even say goodbye. Log C, this, oh, there's two C's, I'll make it a, I need another letter. Give me a letter. Hmm? A? A. Okay. Log A, C. The log of a product is the, somebody was close, somebody said sum? Sum. Log of product is sum of logs. Log of e to the is get rid of the e and get rid of the log. They're inverse functions to each other. Log now, this may not look like an advance. However, it is. Because if I just change letters, you'll know exactly what this is, the graph, what this is, what kind of function this is. Y equals mx plus b. Line. What's the y? The y is the log of c. What's the m? The m is the minus k. What's the x? The x is the t. What's the b? The log of a. Oh. Rather than doing it by hand, this has the option of a logarithmic scale for the y variable. That's like taking the log of the concentration. So I click on logarithmic scale, plot graph. Now, I admit it, I cooked the data. If you got real data from a real experiment, and you wanted to, and you did this, you'd be hoping for a line. Right? So, I know that my concentration is given by an exponential function. Therefore, math tells me the log is given by a linear function, a line. So if I take the log of the y and draw this, I should get a line. As I said, with real experimental data, it will never look this good. But this is a pretty nice line. If I need to know the equation of the line, what do I do? Rise over run till slope, right? And then the y-intercept. Right. So all I need is the slope and the y-intercept. So let's cheat a bit, because we don't want to spend a lot of time on this. I'm just going to take a couple of well-chosen points to give myself the rise over the run. Log, and remember, it's the log for the log of, where'd they go? 4.22 minus log of 0.76 divided by 1 minus 4. And that equals minus 0.57. That tells me the slope, negative 0.57. And so now you do a reality check and you say it's a negative number, a negative number smaller than 1. It should be pointed downward. Good. It's not too steep. Good. You have to be careful, these are screwy axes. Now you've got the slope, and you already mentioned y-intercept. Luckily, it was given to us to begin with, the y-intercept. It's the log, well, that's a 7 point whatever up there, but the log of it. So, here's the equation. C of t equals, now I've skipped a step. I really should be solving for the log of a, but it will turn out that the log of a will give me an a, which is what I'm really after, that's equal to the initial value, 7.2. The critical thing is I have my k. So by doing the transformation, by taking the logs, you end up being able to stare at a line and figuring out the critical thing that you need, namely the k, from looking at the line. And as I said, in a real experiment, if you were doing this, and you may well do this in a physics experiment, I'm not sure in a biology experiment, it depends on the class, but you could be fitting a line to a bunch of data points just by hand, with a ruler, looking and seeing what's a good fit. Or you might run some software, which, of course, is available. It's not secret. These squares, it's called. But we have our equation. And now, oh, the punchline. How do we find when it hits 0.25? Solve for t. But depending upon how you feel about algebra, this may either be the part that you love or the part that you hate. Is it obvious what you're going to do? Kind of. Semi-obvious? 0.25 divided by 7.25 equals e to the minus 0.57 t. On both sides, yes? So this is the log of e to the is to the, and now you can sort of divide by 0.57, that logarithm over there, and you'll solve and get t is approximately 5.99. So if you guessed 6, you wouldn't be far off. Another thing, I'll also, here's a very simple to use plotter. This 0.57 is, that's right. So this is also, this is a plotting tool that's really easy to use, and you'll be able to use this on one of these assignments. But here's the graph of a function. And you can graph more than one function and see where they intersect and things like that. So that's one kind of population model. What's wrong with exponential growth as a model of, say, human population? Or maybe make it a little less personal. Say you're modeling the population of some kind of could be a rodent, a bird.
Every population some sort of carrying capacity, so at some point they'll run out of resources and they'll have to shrink.
Oh, darn. You know about carrying capacity. So this is actually good because we're going slower than I thought we would. What she's just mentioned is a way that population's constrained is resources. So the resources could be in terms of food, could be in terms of space. Every population is going to be constrained. Essentially, every population is going to be constrained eventually. And so how do you take that into account? You introduce some sort of change to the exponential function in order to come up with a more realistic sort of description. Now, in population biology, there are all kinds of models, all kinds of approaches to this. The one that you just mentioned gives rise to something called the logistic growth model. Now, since this is a calculus-free presentation, we don't know what this is. We do know what this is. This is our population, our exponential population model. This is actually the derivative of the population function with respect to t. So dp dt. And the way you read this is the rate of change of population with respect to time is proportional to the size of the population. That's the exponential growth model. It gives rise to this exponential equation. Now, as was just said, read in this next paragraph. Of course, most populations are constrained by limitations on resources, even in the short run. And none is unconstrained forever. The following figure shows two possible courses for the growth of a population. The green one is exponential growth. The blue one reflects what you just mentioned, namely a population that starts off growing like the exponential curve, but soon diverges from it and is constrained by what's referred to as the carrying capacity of the environment. Now, where does this curve come from? There are different ways you could answer the question. One is, I think that's what the population will do. So you just drew it. A way you can derive this is by changing the model. Instead of the rate of change of the population just being proportional to the population, you change the formula for the derivative. And what we do in Math 115 is we come up with this, and we explain where this symbolism comes from. You don't just pull it out of the hat. It might seem like that the first time you see it, but you stare at it long enough, and this becomes a sensible sort of mathematical expression. It says that you modify the rate of change by multiplying the factor that you had before by something that accomplishes mathematically exactly what you wanted to accomplish with your carrying capacity. And this gives rise to a different kind of solution. And what's really amazing, this is an extremely simplistic model. But the person who developed it wanted to apply it to the US population. So the data points used to develop the equation were just these 6 plus assumptions that led to that form for the derivative. And this would give rise to the red curve. The data points are just the blue points. They stopped being real in 1840. But it stayed accurate until 1940. Those are the US population dots following his red exponential, they're just the growth curve. But then Oh, darn. There it goes. The U.S. population takes right off after about 1945 or so. Certain significant historical events might explain part of what happened here. But it's pretty clear that his graph stopped being a good graph. Well, I just wanted to show you. Sometimes exponential growth is sensible for quite a while. This is a picture, well, it's a very bad picture, of an algae bloom off the coast of China. This is caused by both chemical and heat pollution. It's stunning in its size. It's also deadly because algae consumes oxygen, which means it's not available for any other organism. And sometimes you just have to wonder, what are they thinking?
Oh my God.
Oh,
No, we don't do that.
Algae's got a lot of sort of biological activity going on. It's not like swimming in some kind of sterile water. If these guys have any cuts, sores, or whatever.
So guys, the interesting thing here, if I could just interject for a second, is between the three of us, we each see this picture and each see different things. I look at the biology that's happening here and think about the toxins that this algae is producing, as well as the amount of oxygen that they're consuming. Dr. Duffus looks at it and might be considering some of the mathematical equations that are happening here, the growth of the algae, things like that. Dr. Gordon looks at it and sees, what do you see?
I'm thinking about the population and who is going to be swimming in this water and why would they be swimming in this water and what the motivations that they.
And this is all part of you becoming a scientist. As you become a scientist, you will look at this and you will see different things just like we do that interest you and go, I could study that for a while and I think that's really cool and amazing. And that's something that we're going to talk about more as you go through GLUE. Sorry.
Oh. Okay, so. Oh yeah, this is all really taken. So I'm going to do this quickly. I think it's fun. So, have you ever had the anxiety dream you realize you've forgotten to take the final on a course? Or you're about to take the final on a course you've forgotten to go to? For professors, it works the other way around. You dream you're giving a lecture for a class that you know nothing about. Closer to the truth than you may want.
You're not supposed to find that out till later.
But one area, namely the second main area where math gets applied, is probability theory. And this is one of those things that a lot of mathematicians don't study very much themselves. And when they first come to teach it, it can be quite confounding. Perhaps the most pulse-quickening topic of all is conditional probability, the probability that some event A happens given that some other event B has happened. It's a slippery concept, blah, blah, blah. No, just scan this last paragraph. Before going on vacation, you ask your spacey friend to water your ailing plant. Without water, the plant has a 90% chance of dying. Even with proper watering, it has a 20% chance of dying. The probability that your friend will forget to water is 30%. What's the chance your plant will survive? If it's dead, what's the chance your friend forgot to water it? If your friend forgot to water it, what's the chance it'll be dead? Now, my reaction to reading this is it would be easier to either get a new plant or get a new friend rather than to figure out what's going on with these conditional probabilities. However, I can't resist. So let's just do something simple. And then I'm going to show you how we might apply it to something a bit more serious. And we'll only take conditional probability. These card things. So I get to turn over a card, not replace it, turn over another. What's the probability both cards are aces? Now, there's lots of ways to think about this and to figure it out. I want to illustrate one. We make something called the decision tree. And card games are the simplest, or maybe flipping coins. These are the simplest sorts of problems. Now, along the edges of the tree, we're going to put probabilities. The probability of the event at the right end occurring. So what's the probability? Oh, for those of you who've never seen a deck of cards before, 52 cards, 4 suits, aces through kings. What's the probability of turning over an ace? 1 out of 13 or? Right. A lovely thing about decision trees is when you add up the probabilities branching from a point is they add up to 1. The probability of not getting an ace, 40 out of 52 or 12 out of 13. Now, the hard part. Second card. Ace, not ace, ace, not ace. The probability of getting an ace, given that you had an ace the first time. 51. I spent too much time gambling, probably. 48 out of 51 the other way. These are called conditional probabilities. Probability second is ace, given first is ace. So I'm just abbreviating this randomly. And then down here, the probability the second is an ace given the first isn't. 4 aces, 51 cards, and 47 of them. Now, there's only one way to get to 2 aces, and that's to follow this branch to the end. And we multiply the 2 probabilities along with it. 4 out of 52 times 3 out of 51. What we're actually multiplying is the probability that the second is an ace given that the first is an ace times the probability that the first is an ace. And that's equal to the probability that first is ace and second is ace. Okay? Nothing up the sleeve. No, haven't done anything illegal yet. Okay. So now we're going to do something else. The probability of having a disease, leave it unnamed. It's fairly uncommon. 0.8% of the population, 0.008. So we have a population, the disease proportion is just 0.008 of the entire population. I'll tell you some more information. The probability of a positive test, so this is the kind of disease for which there is a medical test. The medical test isn't foolproof. The probability of a positive test, given that the disease is present, is 0.90. So I'm making these up. This has got a name. In the literature, this is called the of the test. Now, here's a different. The probability of a positive test, given no disease present, is 0.07. This is called the probability of a false positive. So that's all the information we have. Now we would like to answer the question, what's the probability of a disease being present given that the test is positive? Oh. Without some kind of a roadmap, this is not going to end happily. So let's do a tree, and maybe hopefully we'll be able to populate the tree with enough numbers that. So first division is disease, no disease. So this is the disease step. And here we put the probabilities that we were given. And what's this one? 1 minus 0.008. Now we conduct the test. Positive, negative, positive, negative. We do know some of these numbers. The probability of a positive test, given that the disease is present, there is a sensitivity. That means that this one has got to be 1 minus 0.9. The probability of a positive test given no disease, 0.07. I want this conditional probability. If I follow the reasoning up here, what I'm after is the probability of disease given positive test. That's what I want, times probability of positive test equals probability of positive test and disease. And disease. So we should know 2 out of those 3 numbers. We'll be able to find them. What's the probability of positive and disease? What's the probability of positive? Then we can figure out the probability of disease given positive. So how do we get it? Well, positive end disease multiply 0.90 times 0.008 is 0.0072. See, we did exactly the same thing as we did up here. To get ace and ace, we took the probability of ace given ace in the first times the probability of ace in the first. To get positive end disease, we take the probability of positive given disease multiplied by probability of disease. Okay. Uh-oh. Probability of positive.
We multiply the two positive if disease is present and if disease is not present.
So here, you, I don't know if it's simpler to think of the aces or just to think of this situation. The way you compute the probability of a positive test is add the probabilities associated with the branches that lead you to positive. So that would be this one, 0.0072, plus this one, 0.992 times 0.07. That's how you get the probability of a positive test overall. And that number is 0.0766. This is the number we want. So we divide 0.0072 by 0.0766 to get the number we want. Question mark equals 0.0072, 0.0766, and we get 0.09. So the probability of the disease being present given a positive test is 0.094. Chances of the disease being present is less than 1 in 10. So this is called the rare disease example. And in every class where you study conditional probability, and anytime you study probability, you study conditional probability, they trot out this example to give an indication of the importance of reasoning with conditional probabilities. Because if you were in the position of receiving the news that you have just tested positive for, you might be quite concerned. This seems to be giving you reason to be at least not suicidal at this point. Maybe another test is in order. Not convinced. These aren't unrealistic numbers in terms of sensitivity. In fact, these are quite accurate tests. As tests go. 1.4%. So, your assignment. You're free to think about this if you like. There's an assumption being made here that's very significant that's led to this conclusion. All of these values we can take to be correct as far as this toy example is concerned. The probability of a positive outcome given the presence of the disease is 90%. The probability of a positive outcome given no disease present is 7%. 0.8% in the population overall. So there's an assumption being made here behind this calculation may not be so clear. And I'll give you a couple of postings that discuss this issue. Okay. Here's the hint. This is the probability of the disease being present in the population. This probability and this probability are being computed With what population? Poor population? So maybe there's an issue. So, conditional probability, I thought about this a bit before I presented it to you. This can be really a confusing topic because the language gets mixed up with the math concepts, and you have to go back to the definitions of the math concepts, which we haven't spent much time on today, for this all to make sense. But I haven't lied to you about any of the mathematical derivation here. These calculations are all okay. It's just that there's an assumption here about these conditional probabilities and the populations involved. It's very important. Okay, so, any questions? How do you like Emory so far? You been here since Saturday or Friday?
Friday.
So they've gotten to spend one day by themselves yesterday in the tower. Apparently, maybe didn't make it MARTA the way they wanted to, but they'll try that again. So, so far so good.
Which tower?
Claremont.
The new one?
Well, no, it's an older building now.
The one that used to be graduate
Graduate students, yeah.
Has it been refurbished since then?
No, not really. No.
Okay. If you have any questions about placement or math classes to take or not, you have to answer them. If you just want to stay and ask. Okay. If you feel like leaving, where's there to go now?
Back upstairs, W501. You guys don't have any questions about math at Emory?
So say you're taking math 115 and 116. What are the first few concepts that are taught with them?
Same as Calculus 1. So we do a whirlwind tour of pre-calculus, 3 days of fun with trigonometric, exponential, log functions, and reminding you about graphs and that kind of thing. And then we do limits and derivatives. Then diverges from standard calculus because we talk about population models. We do maybe a fewer applications of state integration to I don't know, standard physics things, and do more on biology. So it's really a lot like Cap 1.
Okay.
It's not too.
Is there a placement test for math classes?
No. The reason that there isn't, well, is we don't teach a pre-calculus class. So we thought about having a placement test, but then the outcome would be, oh, let's see, pre-calculus skills we don't have a solution here at Emory. You're going to need to take a summer course somewhere. So no, we don't have a placement test. Almost everybody who enters here has the background to start in calculus sequence. Or to do probability and statistics. You certainly have the math background to do QTM 100 or Math 107, which is the province that. Have you seen Alex? Not in person. You saw him.
Oh,
They see that on Wednesday.
Ah,
But that is something that you guys have an advantage over a lot of other people, is that you have 6 weeks of Alex Calc 1 with limits prep paid for and ready to go starting on Wednesday. So along with the tutoring that you already know about, which will start tomorrow night, so you guys can get ready to go whenever you hit the ground running in the fall.
yeah, Alex, I'd be very interested in your reactions to using it. We have very little experience with that sort of adaptive software. It's supposed to be an effective way to review pre-calculus concepts and keep test you along the way. So please let us know what its strengths and its weaknesses are. So, one of our instructors is here today. Steve will be leading some of the tutorials. So he is a resource, a bona fide PhD. Well, I guess not officially. Everything with the official blessing, right? Did you write it?
Yeah.
Oh, you did?
Yeah, that's your real deal. Cool.
He got, okay. That means he's being drastically underpaid for what he's doing.
Yes, it really does. Sorry, Steve.
Yeah. So the tutorials in the evenings, we hope that you'll be able to make use of them, that you won't be so exhausted that the last thing you want to do is ask questions about math. But they're 3 evenings the first 2 weeks and 2 evenings the last week. And be free to come and ask questions. Steve is there as a resource.
Yeah.
I should be calling him Dr. LaFleur rather than Steve.
Steve is fine.
Steve is fine.
I'm also interested in what you think the degree of difficulty or silliness of the assignments is. Just me. I don't really have a good gauge on how hard they are. The intention is that are the groups that the students work in, are they constant through the program, or does anybody even know about the groups?
They don't know about the groups yet. The math groups will be the same though. We'll keep those things constant because those are things we can look at later. Yeah.
So there will be a posting of 3 assignments. And of course, so the group is supposed to produce a solution set. These are not really long, as far as I can tell. It should be quite reasonable, especially if there are 4 people in a group working on the solution. And here too, I'm really interested in what you think the degree of difficulty is, and how confusing is it. Any other questions? We're not still being taped.
I can shut it off. You've got something particularly interesting to tell them.
I just wanted to tell you the truth about math.